Um, so today's in the lab. So we will talk something about lab. We will go over some topic here, and then we'll go to the Excel. So we will talk about the theory first, and then we'll do Excel. And I know that we don't have because of the typhoon, so we have one class less. So next Monday we will be in the lab again. So I think I booked this room again. So maybe next Monday you come to this room. I'll make a announcement in the blackboard again. Just to remind you that the homework is due on Sunday. So make sure that you finish your homework. So today's goal is to finish half of it, and then we will try to do some Excel because we're in the lab already. So just very quickly review the idea hypothesis testing, okay? Because we will be using this again, okay? So basically that what we have is the idea of hypothesis testing is you have something to test, okay, which is H null, and assume H null is correct. You derive the test statistics, and you see whether the test statistic is above the critical value, or the p-value is larger or smaller than your significance level alpha, okay? So we have two different ways to do it. One is by the z-test when you know sigma square, otherwise you do t-test, okay? And in general, you don't know sigma square. So basically in the real world, you do a t-test, okay? But for sample proportion, because of mean and variance are related, okay? So that's why when you do hypothesis testing for the proportion, you would be, it's okay to use the z-test, okay? And now I want to come to the two samples, okay? And you notice that the idea behind two samples is exactly the same as the way that one sample works, okay? So let's go ahead. So what we want to do now is compare the mean of two samples. I think I explained already in the last class what is the purpose of doing that. It is because of the fact that you're trying to see where the difference between two populations, right? Say whether the GPA, say boy and girl are different or not, right? In the gender study, okay? So there are two cases. One is you assume equal variance. The other is you assume without equal variance, okay? And as we said, we are not going to give you the idea why we have that formula, but I just want to remind you that the second one is more general than the first one, okay? Because the first one is assuming equal, okay? The second one is more general, okay? And the next thing we will discuss is compare the population, okay? So this is a two extreme case. The first extreme case is independent population, which means that they're completely unrelated, okay? And the other one is called pair population, is perfectly related, okay? So for each observation in population 1, there's a corresponding observation in population 2, okay? So for example, in what sense you have that is like, you try to look at the effect of medicine, right? You take one subject, right, and do the measure, right? And then maybe give him or her some medicine or give him or her some vaccine. And after the treatment, you try to do it again. So for the same person, you have two observations, okay? So the two observations fully, should be correlated, right? So you would care about the difference of these two observations, okay? And that would be the the measurement. Okay, we need. Okay, so that is the most special case. Okay, the paired, and these two are another extreme. Okay, so the two extreme cases. So let us review this extreme case. Okay, where the two populations are completely unrelated. As I mentioned, the example whether it is boy or girl, maybe people, Asian people or American or European, the races, these can be, you can consider them independent, okay? So the question is asking they have the same mean, population mean, okay? And assuming your equal variance, okay? The T statistics is following this, okay? I'm not going to explain why this formula is right, but very roughly speaking, because the mean of the sample mean, okay, the sample mean of population 1 and 2 by central limit theorem are normal, okay. So the difference between normal is also a normal, okay. So the only thing you need to worry is about how to get the denominator right and how to get the degree of freedom correct, okay, which is something we're not going to explain, okay. But just you can imagine this is normal, okay, and the difference between two normal is still a normal. So just very roughly speaking, it's like this, okay. Remember when we learned before, it's like x1 bar is like this, right? And x2 bar may be different, whether the same or different mean, right? X2 bar is like this, okay? And take a subtraction, x1 bar minus x2 bar, because normal is still a normal, okay? So the null will be saying that under the null, it is 0 here, okay? So you, as a two-side test, you want to see if this is follow the rejection region, the green area. If the data source is in the green area, right, that means that they're two different, right? So that is the idea. Okay, this is two-sided test. Of course, you can do one-sided. If two-sided, you put alpha over 2 on the both side. If one-sided, you put only alpha over just one side. Is that okay for this one? So this is how to do transformation is doing from here, right? When they're same, it's just 0. Right, so it's basically this guy over this guy, okay? So, and the critical value is given by this and alpha over 2 on the both side. Okay, so that is that's how you get this critical value, right? This T, okay? And just to remind you, what is S1 square and S2 square is the weighted average, okay? So look at the formula carefully again. Maybe I just slowly go about this formula. So what is this formula? Okay, you can see this is the idea behind this formula is the following. So remember now you sum from population 1 and population 2. Okay, and population 1 we have a mu1 and mu2, right? They may have same mean and different mean. This is something we want to try to see. But what you are making now is they have the same sigma square. Okay. So remember when you do the sample variance, right? S1 from the sample from first population, right? S1 square is already a good estimator for sigma square, right? The sample variance you obtain from the sample 1 would be a good estimator for sigma, okay? Right, because just one sample, right? You take the sample variance is the good estimator for the population variance sigma, okay? Same for this, same for the S2, right? S2 is also a good estimate for sigma square, okay? Two of them are good estimate for sigma square, okay? Now we have two estimates, okay? Both of them are good. Can we combine them in a good way to improve our accuracy, right? The idea is saying, okay, you use the first population, you figure out the same. The variance is like 20, okay? The other one, you figure out the sample variance is 10, okay? If they have the same sample size, right? You think both of them are equally accurate, then what you think is the best estimate is 15, right? Middle, with the midway, right? But if the, say, the sample variance 20, the first one, have more sample, right? Then you think that should be more accurate. You should bias towards against it, right? You should get more weight on it. It should be more closer to 20 than 10. Okay, that's the idea here, right? When N1 getting bigger, okay, the new estimate would be bigger, closer to S1 square, right? When N2 is getting bigger, the average will be closer to S2 square, okay? So SP square is just actually it's just a weighted average between the two sample variants, okay? And the weighting are given by the sample size, okay? And is that okay? So that is the idea. So basically, that's how you get the formula, okay? So let me very quickly, like a whiteboard to explain little bit math very quickly, okay? You don't have to fully follow if you don't follow, but just very quickly for those who like the math is very quick, okay? So x1 bar, according to central limit theorem, will be this, okay? Since you assume that they have the same variance, okay? So that's why the sigma is a sigma 1 square, okay? And by central limit theorem, you also have this, okay? So this is what is saying the mean of the sample, right? Have a normal distribution. The question is asking you whether mu1 and mu2 are the same under the null, okay? But first note that because the independent, that's important assumption, independent, okay? That means that the covariance is 0. So the difference will be mu1 minus mu2. And because they're independent, you just add them up. Okay? So under the null, this is 0. So that's why you have normal 0 as okay. So if you know sigma, right, this z statistic is very simple, right? Because if you suppose you know sigma, which we shouldn't know, but suppose we know, then the test statistic is just like this, right? You just will be x1 minus x2 over sigma. We have this easy, sigma square n1 sigma square n2, right? That is supposed to know sigma. That will be our test statistic, okay? There's a z-test, okay? But we know that we never know sigma, so we have to use t-test, right? By t-test, it's just replacing the sigma by our estimate, right? So basically just SP over there. So that's how the formula comes in, okay? So that's why when you don't know, use t, okay? The same thing, but you have to change to the S, right? Our estimate, and our estimate on this is just, as we said, the average of what we actually estimate from, you can say SP, maybe less confusing. Let's use SP. Can't write here. Okay, so that is exactly what is behind why that formula is right. Okay, but I'm not going to explain further why this is. But in case you are interested in, actually it's very straightforward, the proof. But I'm not going to do any more because I just try to convince you that this is right. If you don't follow, it doesn't really matter because we are not doing the math part. Okay, so if you get it, you get it. Don't get it, doesn't really matter. Okay, so just to remind you what is confidence level here. Okay, common interval here is, when you talk about mean, it's same as the hypothesis testing, okay? So this guy x1 minus x2 is the numerator. Look at the last page, the numerator, okay? Let me yellow this guy, okay? Yellow this guy, okay? The same is here. This is 0, right? So it doesn't really matter. So yellow guy here, okay? And look at this. Here, the critical value is here, okay? The last part, blue part, check carefully. This is the denominator of the t statistics, okay? It's always like this. If you look at everything we have done, okay, for the sample mean, okay, and when we talk about confidence interval and hypothesis testing, is always like this, okay? Just above plus minus. How to derive this? Same logic as we have done, okay? Because you can imagine x1 bar minus x2 bar is a random variable. It's a one thing, right? It's a one random variable. So everything remains the same, okay? Just replace things. Is that okay? I guess it would be easiest to look at the example because I think example can help a lot, okay? So assume that you have two populations, we have the same independent, right? Independent population have the same population variance, okay? So that's the same sigma, okay? And you know it already, okay? The next part is probably you want to know whether they have same mean, okay? And so the question you have is the sample size is 50. Sample mean is 40 and S1 is 4, okay? And the other one sample size is 40, so N2 is 40. So all this number, okay? So the first thing you want to do, okay, you want to do this two-tailed test, okay? Now the question is you have S1 is 4, S2 is 3, okay? So that means the following, right? It means that S1 square is 16, right? And S2 square is 9, okay? So these are two numbers and they are both good estimate for sigma, right? Sigma square. So the question is which one is the best, okay? Both 16 and 19 are unbiased estimator of sigma, okay? But it's easy to show they are not the most efficient one, okay? So you want to improve the efficiency. How do you do that? Do the average, okay? That's why you want to do average is because all of these are unbiased estimator, okay? But you want the one that has more efficient. So that's why you use this one, okay? The thing is like, okay, why don't I just use 16? Can I use 16? Yes, you can use 16. Can I use 9? You can use 9, okay? But that is not the best way to do it, okay? When not the best way to do it, that means that your type 1 error and type 2 error are not the best, okay? If you do the better way, alpha and beta, the type 1 or type 2 error can be minimized, okay? Because as I said, when you do the best policy, the best thing to do, alpha and beta has some trade-off, okay? If you don't do the right thing, then the alpha and beta actually can be go lower, but you didn't, okay? So that is the best way to estimate because you improve using a better error, then of course you get a better result, right? So this is just N1 minus 1, N2 minus 1, N1 minus 1, okay? Average over the sample size. And this is S1, okay? This N2 minus 1, N1 minus 1, N2 minus 1. So this is waiting for the second one, okay? So this waiting for 16 and 9, so it's 12.89, okay? And so basically just in the midway between the two, right? So 9 and 16, and this is 12.8, okay? So you can see it's closer to 16 than 9, okay? Now, this is the our estimate for sigma is a better estimate for sigma. So everything actually very straightforward, right? It's very straightforward. Why? Because remember the formula here, right? The formula here, we just to rewrite again. X1 bar minus X2 bar, okay? And square root, right? SP square over N1, SP square over N2, okay? So just -2, SP square is 12.8, okay? And you divide it by 1/50 and 1/40, okay? So it's just the standard formula here, okay? And what you get is -2.65, okay? So, and now you get the number, so you need to check out the p-value, okay? So just to remind you, what we are doing here is just nothing but the difference is here, okay? So this is the okay, you want the under now this is 0, okay? And because I said we never do it in this, we do it in the t, okay? And the degree of freedom is n1 plus n2 minus 2, so it's 40 plus 50 minus 2 is 88. Okay. This is 0, okay? And what you have is your data is -2, it's here, -2, okay? And you go down all the way to the t, okay? It's -2.625, okay? So the first question is to calculate p-value, okay? What is this area times 2? Let me repeat. What is this area times 2? Why times 2? It is because we're doing two-sided test, not one-sided. If one-sided, just add this area, okay? Two-sided test is all two-tailed test is always area times 2. Okay, just to remind you, when two-sided test, you have 2 times 2. Okay, if you don't want to times 2, you compare alpha over 2. Okay, because both are over 2. Okay, but as a convention, it just times 2, then you just compare with alpha. Okay, so how to calculate this? Okay, it's good that we have Excel now here. Let's do it. Okay, so this area would be just because it's 88 here. Okay, so will be just T this. Okay, because this is on the left hand side, T this is exactly what we want. Okay, -2.625. Okay, and you tell them degree of freedom is 88. Okay, you calculate area, that's true. Okay, remember you have 2 times. So that is the result for the p-value. Okay, so let me actually do it in the Excel. Since we're Excel. .625, 88, true. Okay. So you can see this is a 1%. Okay. So if you do the 5% significance level, okay, that you can reject. If you do 10%, you also can reject, but 1% you can't, right? Because it's slightly above 1%. Okay, let me repeat, you can reject at 5%, 10%, but not at 1%, because this is slightly more than 1. Okay, so just make sure that you get it. Okay, the next thing is, without going back to slide, you use the t-value method, critical value method, right? So look at TATA, okay? And what we want to do is, let me use the purple color, right? You want to make it purple color so that this area is 5%, so alpha 2 is 0.025. Okay. So because add up is 5%, so actually it's easy to see this guy would be T inward, okay, 0.975, okay, 88. Why? Because the right hand side is 95 to 0.25, so the left hand side is 0.975. Okay, so this actually is symmetric, but you can also do the calculation. 0.025, 88. Okay, so there's two tails, so that's why we have two critical values. Okay, so let me just write down here T inward 0.025, 88. Okay, or you have T dot inverse 0.75, 88. Okay, so that means the negative 2, right? Negative 2.6 is here, and we have 1.9 here. So this blue one, the test statistics is way smaller than the critical value. Okay, then you reject. Okay, so we'll reject the idea that they're the same. Okay, so that is the result of our test. Okay, so that's why we get the same answer here, right? So just to remind you again how the confidence interval and the test statistics are related at the end. I hope there should be no problem. So you will see, let me use green color. So the numerator here is just here. Okay. And the critical value here is just here. Okay. And let's use the red color. The denominator here will be the third term. Okay. So basically, when you did the test statistics, is already did the confidence interval. Is that okay? Now, if that's okay, we go to the another one. Okay. Is there any question? Am I going too fast, or is it okay? Is it okay? Now, we are going to relax our assumption. Okay. We can go back to the whiteboard. Okay. Let me see if I can do copy and pasting. Not really. Okay. So basically, the math is super similar. Okay. I change some or just add some notation here, everything will be the same. Okay. So here, now we assume that actually we are more general. Here we cannot say they're different. So they're the same. So that's why we really need to do the following. Okay. So we can no longer say they're sigma. Okay. So they're sigma, they're different. Okay. So the black thing is a different thing. Okay. X bar 1 is just mu 1 and have sigma 1 square and sigma 2 square. They're not the same. Okay. But the formula below is the same. Right. So everything below will be the same. 1, 2. Okay. And if you know sigma 1, sigma 2, you can also do the Z test. That's no problem. That is very simple. If I told you what is sigma 1 and sigma 2, you can also do the same. Okay. Now the question is how to do the T, right? Because sigma 1 and sigma 2 you replace by S1 and S2. That's it. So that's nothing because they are different, that you cannot come up with better estimate, and that's it. So that is what we have in the second test. Is that clear? This is indeed it's very simple. There's nothing new there. Because the special case, S sigma S1, S2 are basically estimating this sigma, okay? But now you don't have this, so we just use their own estimate to estimate their own sigma, okay? And that's it. Is that okay? Now if you don't really want to care about the math here, just go back to here, okay? Go back to the math, without the math, okay? You can see the same thing here. When the same, this is 0, okay? So just this over sigma 1 squared, sigma 2 squared, okay? Before you can come up with SP, okay? Because they're the same, you can use SP to get a better measurement, but now you don't. So that's why you have used S, okay? The only complication, compare this to before, okay, is this complicated guy, okay? T of V. What is the degree of freedom here? What is the, before is N1 plus N2 minus 2, okay? And we have to be very careful which one to use, okay? In general, this number, the V, will in the next slide, will not be too much different from N1 plus N2 minus 2, as we will see in the example, but they are different, okay? And why they're different is beyond the scope of our class. Even for the introductory statistics in the statistics department, they don't teach it, okay? So it's way beyond our scope to understand why V is like that, okay? We are unable to tell you why. So of course I'm not expecting to remember this thing, okay? So this is, you can just imagine this is just a formula, okay? We're unable to explain why this is true, okay? But this is what the formula is, okay? And the confidential estimate is the same thing, right? Because the numerator, this is the denominator, and this is the critical value, okay? Just repeat here. This is the numerator of the t statistic, right? This is the denominator. The middle part is the critical value, okay? So I guess because, I mean, the technique is the same, so let's do the, let's go for the example before the break, okay? Now, so after the break, we'll do one more test and then we'll go to Excel, okay? So we will in the lab, so we'll do something in the lab. So, but let's finish this, okay? So the idea is not that difficult, okay? Exactly all the number the same as the previous example, but we no longer have the assumption that they have to say they share the same variance, okay? Which is more general, okay? So, and in that case, okay, actually the calculation of t-stat is much simpler, right? So just remember what is the t-stat here, right? Will be just the t-stat will be just under the null will be x1 bar minus x2 bar, right? We just square root s1 square over n1 s2 square over n2, okay? So basically just plug in the number 40 minus 42, negative 2, 4 square over 50, 3 square over 40, okay? So there's nothing deep here. So what you get is negative 2.709. So that's very easy, okay? Of course, the difficult part of this is similar to the first one-tailed test, so it's nothing, just the same thing, okay? Right? The only difficulties lies on the fact that what is the degree of freedom V? The V is a very complicated thing, and we don't expect you to memorize that part, okay? So what you have is that guy, okay? And let's go to the next slide. Okay. And this complicated thing, okay. Of course, with calculator do it, we are not going to do it by our head, okay. And the answer is 87.6, okay. And remember, this has this what we call the floor, mathematical floor, or the round down notation, which means that we only take the integer, okay? We take the integer part, forget about decimal places, okay? This is the floor. This go down the floor. So which means that 87.6, 7, we will take the integer, which is 87. Okay, this is the floor, metal floor. Okay, and that means that, remember what we have in the last few slides, the same question, the degree of freedom is 88, okay, with 87. So actually, yeah, not much difference, right? Not much difference, okay. And well, so then what we are doing now, okay, is trying to do the hypo testing, right? So we know T is last line is negative 2.70. So basically what we have is like this, right? But let me draw here. Okay, let me do it again. Okay, so what we have is supposed to be normal under the null. This is 0. And data you have is -2. Okay, you want to judge where the -2 is far away from 0 enough to say what we want to say. Okay, and you convert to T87. Okay, so there's an interesting part. Compare this to the previous cases. Is degree of freedom depend on the what kind of sample information you get beside the sample size, right? Before, it just only depend on sample size, but now you have to do calculation. Okay, but nevertheless, this is also the mean 0 here. Okay, and the data is -2 here. It convert to, according to the previous slide, is -2.709. Okay, so again, the question is, you either do the critical value method, or you do the you're going to do the area p-value method. Okay, let's do the p-value method first. 2.709, p-value is the green area times 2 is the green area times 2 again, because it's a two-sided test, so you need to have that. Okay, so how to calculate this, right? Just to remind you again, I mean, the area on the left, right? So we just key this and input your number and put degree of freedom 87 and true. Remember, you have 2 times 2 is the p-value. Okay, let me go to the Excel. Okay, so let me do it here. You just key this -2.709, 87 true. Okay, remember you have to multiply by 2. Okay, because this is the, you want to calculate p-value. So the p-value is 0.008. Okay, 0.08. So that means that they this is, you will reject the null at regardless what percent you're using, right? Because it's less than 1%, less than 5%, less than 10%. Okay, so you can even reject this at 1% significance level. Okay, so of course you can also calculate the critical value, right? Critical value would be actually very similar to what we have in the previous case, but now instead of 88 you have 87. Okay. So the critical value is rather simple, right? It's very similar. It's exactly the same as the previous case, but now with 87. Okay. So because of what we get is negative 2.7. Okay. Negative 2 is here. Okay. So with this, the data we have is within the rejection region. So we reject. Is that okay? Is there any question? If no, then I want to go back to here. Okay. Again, I want to say a little bit about the confidence interval. Okay. This is again the numerator of the test statistic. Okay. And this is a denominator. And this is the critical value. Okay. So for the sample mean, okay, it's always like this. Okay. For the sample proportion, you have to be a little bit more careful. There will be some changes. Okay. Because under the null, you have a good estimate of the variance, but when you do estimation, you don't have such a luxury. Okay. There's some slightly different between the confidence level and the hypo testing when you talk to proportion. But I think so far it's okay. Any question? Okay, if no, then I think we just let's have a break, 15 minutes, and then we come back. We'll consider paired population, and we'll talk about XL and R if we have time. So we'll talk about one more test today. We don't want to talk too much. So one more test today, and then we'll talk about XL and R. Let's have a break. You have any question? Just ask me. I just walk around. Hi. So as Thomas, I will just do this test and then we'll try to do Excel and R. Okay, since we're in the lab. But next Monday also in the lab, and just remind you who those arrive late. Next Monday we also in this lab because of the typhoon and everything schedule is like chaotic. Because we didn't want to do makeup class, right? So that's the only thing we can do is just to move things around. Okay. So let me quickly finish this set of slides. Actually, it's very simple. Okay. But I hope you understand the background behind this. The answer is very simple. At the end, as I said, this one actually is the same as the one sample test. Okay, nothing different from everything the same one sample, but I want to explain why we need that. Okay. So this pair, the population is the exact opposite case. We say independent population. Okay, it's another extreme. Right. One is they're completely independent. Now here we are completely related. Okay. What is completely related here is there's two population. Okay. The observation are this. This is say observation before they take the vaccine and this after the vaccine. Okay. So suppose the example is we're looking at how the antibody changes after taking the vaccine. Okay. What we're going to do is collect a bunch of data. Okay. Each individual measurement of the antibody level before they take the vaccine. Okay. And the other side will be each individual, okay, antibody level after taking the vaccine. Okay. So this X11 will be the last is the first individual, okay, before vaccine, first individual after vaccine. Okay. This is the nth individual before, the nth individual after. Okay. And so why we care about this, okay, is because the main thing we care is about difference. Okay. We care about whether you took the vaccine, okay, whether antibody level goes up or down or nothing changes, right? This is usually you compare two groups, okay? Before and after is basis of a lot of scientific experiment, right? Say you want to see, for example, whether you say, for example, right? You use an old machine, okay? Okay, this is the speed of the car, okay? Maybe you're thinking about a Elon Musk, right? You're thinking about a rocket, right? This may be how fast using the old system, okay? And the next thing is maybe he updated hardware or software, whatever, right? This may be the speed of the car or the rocket, right? So you're not Elon Musk, right? And you want to see whether it's okay to adopt a new method, right? What we do is do many tests, right? The same, maybe this is car number one or number one trial, number two trial, number three trial, right? You want to see whether they're different, right? So that is the idea behind you. Many experiments do like this, right? So you have things before intervention, right? And you have after intervention, and you to make things easy compare, you look at, you have the same object, right? Object one you do before intervention, after intervention. Object two the same, okay? And what you care is the difference. So what you care is the D, okay? So basically D is the thing we care, right? So basically we apply one sample test on D, okay? And because we don't know sigma, usually we don't know, so just use the t-test. That's it. I'm done. Okay? So that's why you do the D is the mean of the difference of the mean, right? You just apply one sample test. Right? So nothing is new here. Okay? So you say the difference between this is mu of D, this is the D, right? So everything the same, is D minus the mean over the SD over root n is Tn minus 1. Okay. So there's nothing deep here. This is the SD and there's critical value and the interval estimate. So there's nothing new here. Okay, this is exactly the same as one-tailed test. Okay, but the only difficulty is the data. Okay, the thing is, okay, if I give you different data, right? Every data is D1, D2, D3, D4, then it's just simple. The only thing is how you get D is just coming from the data here. Okay, so the conceptual difference is you are one tail test with one sample test, just starting from here, right? But now we're telling you that, okay, this data comes from X1, X2. Okay. Is that clear what we're doing? Okay. So we just, I have a data, I want to test whether it's 0 or not, right? It means 0 or not, right? And, but this data actually come from before treatment and after treatment, or before experiment, after experiment, or before taking the medicine, or after taking the medicine. Right? So, so let's very quickly. I mean, I don't want to spend too much time on this, but because it's exactly the same thing, right? So what you do is just, oh, the mean is 2. This is basically X bar is 1, right? And this S is 2, right? So basically just apply the formula here, 1 minus 0, right? This guy. Okay. Just I give you the graphic. I'm not going to go to detail, but because it's exactly the same thing. Say now, what you care is instead of X bar, X1 bar minus X2 bar, it's just D bar. Okay, just D bar will be mean 0. Okay, and what you get the data is 1. Okay, so the only question is you transform it to T. This is 0 again. Okay, transform 1, you become 2. Why? D is D bar minus 0 over S over root n. Okay, it's 1 over 2 over root 16, so it's 2. Okay, and then you look at how many samples we have. It's 15, right? So it's T 15 because. Okay, so you want to check the area, but quickly let me do it here. The area here, right? It's 2-tailed test. So it's 1 minus T this through 15 through. Remember, this is the area of the red one. We're doing 2-tailed test times 2. Okay, that should give you 6%. Okay, but let me show you. Okay. Let's do it here. 2 times 1 minus T this 2, 15 through. Okay, so as I promised, it's 6%. Okay, exactly the formula there. Okay, so that is the reason why we have if you're 5%, if you're 5% alpha, unfortunately, you cannot say they are different. Okay, so if you do experiment in this medical test, you cannot say the treatment is effective, right? Although the difference is 1, right? The variance is 2, but you have to do more exercise. Okay, so does that mean if you use 5% as a benchmark, what we're going to do is you have to do more medical tests. Continue to do it, okay, until you really rule out this, make it smaller. Okay, of course, if you do a 5%, then it's different, right? Is that okay? And here I do a 2-tailed test. Okay, you can imagine that maybe sometime 1 tail is more relevant. Okay, so just explain the reason again why you need one tail or two tail. Okay, so maybe if the medicine is you don't know the effect, like Chinese medicine, sometimes you don't know the machinery of the medicine, right? Then probably may correct you if I'm wrong, but you have to do two tail tests, right? You don't know whether actually say you look at the medicine, basically that maybe reduce the blood pressure, right? And then actually you don't know actually is it increase or decrease, right? So you two-sided one, right? And when you use one-sided, suppose the question is asking is vaccine, right? The thing is like if you take one shot, right? You have some antibody level, right? And you take two shots, you should have increase, right? So if population 1 is only taking one dose of vaccine, population 2 is taking 2 doses of vaccine, right? Then the hypothesis testing should be a one-tail test, right? Because you don't expect that taking 2 shots have lower, right? So you put all the probability on one side, right, instead of both sides. Okay, so it really depends on what is the purpose of your thing. Okay, and I'm not going to do the critical value. I think that's fine. Right? Critical value, just look at this and you take out this is a 2.31. So again, you don't reject. Is that okay? If that's okay, let's jump to Excel because I guess we are in the room and then it's in the morning. You may be tired or whatever reason. Let's do something to wake you up a little bit. So we will. There are 2 more tests, but we'll do it next class. So let's do some tests. Okay. So what we want to do here is a one-tail test. Okay. Let's open Excel first. Open Excel. Okay. So here is a test is you give the data, you give the mean, you give the sigma, okay? This will give you the p-value, okay? So let us look at the data, okay? So let's do a one-tail test, okay? Then open a complete blank stuff, okay? So this is X. I think we can start doing this, okay? Just randomly put some number here. Okay? I don't care what number, just put up some number here. Okay, this is data. Okay. And then the hypothesis testing, we have some mu here. Okay. And we're doing C test, we want to do some sigma. Okay. Now, let us do the following. Okay. Suppose you hypothesize the mean is like 4, say, for example. Okay. Sigma is 2. Okay. We want to do a hypothesis testing. Okay. And let us not to follow what the Excel thing first. Let's do it by ourselves, and then we use the formula, and then we'll see how do we do it. Okay. So this set test statistic set Z is what? Z will be just remember the formula. We're doing one-tail test, right? We know the sigma. So remember the formula there. Z will be just X bar minus mu over sigma over root n. Okay, this is the formula if you look at the slide, right? At the very beginning of the slide. Okay, so first we have to calculate what's n first, right? Because we have sigma over root n. So n, we just use count, just counting all of them. Okay. Formula here. Let's move a little bit. Okay, so this is the count. Now Z, I hope you know how to do it. Okay, just this minus this over there. So basically, it's just maybe we have to do X bar first, right? X bar is what? X bar is the average, right? So this is the average here. Okay, so we need to calculate the Z, the T statistics, right? Will be X bar. Let's say as a bracket, because numerator X bar minus the mu, right? And over denominator is sigma over root n. Okay. So this is the Z value. Is that okay for this one first? Okay. So we are now teaching you how to do hypo testing hand by hand. Okay. Let's start with data, and then we construct our hypothesis, the yellow one. Okay. And then we calculate the test statistics. Okay. Now I want you to now I test statistics. So let's calculate the p-value. Okay. What's the p-value here? Okay. And suppose we are doing a one-tail test. Okay. We do one tail. Okay. That p-value, there are 3 different levels, right? P-value. We can have the left tail. Okay. We can have right tail versus both tail. Okay. First, remember what is this here? Okay. It should be 0. Okay. What we have is 0.667, right? And the left tail will be just error on the left, right? The right tail is error on the right. And both tail, we just look at the smaller side and times 2, okay? So let's do the left tail, okay? Left tail, we just norm as this, okay, of this number. Okay, this is the left tail. And right tail will be just 1 minus norm I left you to do the both tail. Okay, you should be able to do it. How do you do 2 tail? That's how you do 2 tail, right? Just on this side, multiplied by 2. That's it. Is that okay? Now let's use the Excel formula. We call the norm test, C test. Okay. So use the idea we call the Z dot test. Okay. So let's do it. Z dot test. You put the set of data, put the mu, and put the sigma. Okay, so as we require, let's use other color. To green, light green, yes. Okay, as we see, the z-test will give you the right tail area. Okay, the right tail p-value. Okay, so from this, immediately you know you can't reject this, right? It's too big. But this is the first formula we have, how to do hypothesis testing. Very quickly, of course, either if it's so simple, we can just directly this. You can skip all the steps if you just require the right tail. If you left tail, just the reverse case, right? And for the both tail, you just depend on where you are, you multiply 2. Is that clear? Is that clear how you do this? Okay, this is a z-test. If there's no question from you, okay, this I think this also I did already. Okay, and one sample t-test we also want to do it, but there's no formula. But let's do it directly. Okay, so this is the z-test. Let's do the t one. Maybe we can just do it there. Okay, we can just do it on the right hand side here. Maybe just go down. Maybe it's a bit better. Maybe just I call it the z-test. Okay, maybe I open another one. Call the t-test. Okay. Let's do it together on how we are going to work out the t-test. Okay. So the main difference between the z and the t is we no longer have the sigma, right? So what we have is we no longer have this sigma, so we no longer have the yellow thing here. Okay, that's no fear. We will have s. Okay. This s. Let me clear what we don't need. Okay, let's clear what we don't need here. Let's clear. Okay. So s will be something we need to calculate. Okay. S will standard deviation sample of this guy. Okay. So this is estimate, and it's just same as we use the count. Okay. I think I should let you do it. Okay. What's the t here? I let you do it. Otherwise, then I do it. Okay. So basically, what I'm asking you is to repeat what we are doing, okay, but using the t. Okay. I just let you do it. Otherwise, you don't learn. Okay. I give you 5 minutes, you do it. So you can just copy what we have and just recreate everything from scratch. Don't look at my slides, otherwise you're just copying, you're not learning. Hope that you can work it out. So I just do the n first. Oh, I should open this one. Okay. Next bar should not be difficult. Just average. Okay. And t will be just so this is the same as before, except that we no longer use sigma, use s. So they're exactly the same thing. There's nothing new here, right? There's nothing new here. The same formula. If you compare this and that same formula, nothing changes. Okay. And the p-value will be the same. Okay, but use t-dist. Okay. And degree of freedom will be just n-1. Okay. And 1 minus. Okay. And both tail will be, because we are on the the t is more than 0, you just multiply 2 with the right tail. Okay. If t is less than 0, then you multiply 2 by the right tail. Okay. So that would be the idea. Is that okay? So you can do this by hand. Okay, it's nothing new here. Nothing deep here. This is a rather simple cases. Any question? Okay. If no, we want to show you the more interesting thing. Okay, is we have is that okay? Is that okay? I hope that's okay. Let me save later. So the more interesting thing is called t-dot test. Okay, the t-dot test by default is it's rather complicated. Okay, okay. So actually there's you have to input 2 data. Okay, and you have tell them whether you do a right tail or 2 tail. Okay, 1 is right tail, 2 is 2 tail. Okay, and you have 2 here. Actually, this is called the equal variance, and later you will see if you put 3 will be unequal variance. Okay, and you can imagine 1 will be a paired test. Okay, so let us do it one by one. Okay, and we do it from scratch. Okay, again, 2 sample test. Okay, so what I'm gonna do is I just get the x there, x1 here, I have x2 here. Okay, what data we want, just randomly put some number. You can put whatever number you like. Okay, so these are the number I randomly. You can put in whatever number you want. Okay, so let us do the equal variance first. Okay, equal variance. Okay, remember how to do equal variance? Okay, so difference is 0, so we don't need to write that. We just test the difference. Okay. So what we want is the following, right? We need x bar 1, x bar 2, right? S1, S2, SP. Actually, we don't have the same number, so we just maybe we just get more. We just add more number here. Okay, we just add more number there. Okay. So we need to have this, and we have N1, N2. Okay. And then we'll come up with the T. Okay. Then we have a P value, left tail, left tail, then right tail, okay. And then both tail. Okay. So let me do the first thing. That's very simple, right? X bar is just average of the X, right? Let me copy this and you see what I'm doing. Okay. Then X bar 2 is just average of X2. There's nothing new here. Okay. S1 will be just standard deviation sample of X1. Right. S2 will be standard deviation of S2. Okay. And N1 will be just count of A. So let me stop a bit here to see if it's clear now. You can try to do SP, okay, and that should, and then do the T and do all the rest, okay. So that is the weighted average between S1 and S2, right? If you remember. You don't have to follow my number, I mean, but this is just a formula. You can do whatever number you like, okay? So if you don't like, actually you can do the square version, maybe easier. If you think that will be easier, you can change to VAR. I mean that may be easier way to do, because I think the formula you have is the square version. So let's minus 1 over this plus this minus 2 this minus 1 over this guy. So this is the formula, right? Just n1 minus n1 plus n2 minus 2 times d3, right? And then d6 minus d5 plus d6 minus 2 times d4. Okay, so that would be the formula. Okay, just slowly check, then would be the same formula as we have. Okay, t will be just x1 minus x2 divided by square root of this multiplied by 1 over 1 over. So the difficult part is to make sure that you get the bracket correct, right? Because this is the formula is like this, right? If you remember, let's write down the formula in case you forget. Is okay, so that is the formula. SP squared times okay. So there's the formula. And what's the p-value, right? That is simple. Left tail is just t this of this guy. Degree of freedom is n1 plus n2 minus 2. So n2 minus 2. 2. Okay. And the right tail, you have to be lazy, you just take 1 minus the left side, right? And both tail will be just this times 2. Okay. So smaller because I want to do the t-test. Okay. So it will be t-test, okay? x1, x2. Let's do one tail. Okay. And we are doing type 2 here. Okay, so this is the same. Maybe I just move it a little bit. This is the right tail. Okay. They do the left tail. Interesting. The left tail thing. And I also can do the both tail. This t-test of this and this, and I two tail, and equal variance. Okay. So you can see the same answer here, these two tell the same. Okay. So that is how you got your two sample t-test. Okay. You can try the case where we talk about the unequal variance, right? And you unequal variance, you just change 2 to 3, right? Then you're done, right? The last digit. If you use Excel formula. If you don't use Excel formula, then we have to a little bit careful. How do we proceed? But I can do it on the. Is that okay with this one? If you do it by hand, the difficult part for the unequal variance is the degree of freedom, which is a monster. But is that okay? You can try, okay? But you can try to do the unequal variance, okay? Let's put it here. Okay. If you do the t-test, unequal variance will be here. Maybe erase the drawing. Okay. This you will do the same, right? Just copy everything here. Okay. Actually, there's no difference, but let's do it again. This average again is here. Okay. And average of x2. Okay, this is the same, the variance dot s and variance dot s for the column B. Okay, and n1 just count, there's nothing deep here, I just do it again to make sure that you have me. Okay. So do note that the formula, you don't need SP2, so we really don't need that one. You can just go for T. Okay. What's T here? T will be just very simple, right? Just x1 bar minus x2 bar, right? And what we have is SQRT will be just over itself plus this over itself, right? Why this formula? Just to remind you, just T just sorry, I should write white space, but this is the formula. Okay. So maybe I just, oh, sorry, my bad. Okay. So that's how you got the T. Okay. The only thing we need to do is the degree of freedom V. Okay. V is a super complicated equation. We'll finish this and then we could go. So sorry, if you want to go, you can go, because just input this formula. We need to. It's super crazy. Okay. But we need to do it. Okay. But do note that the denominator, the numerator part, okay, is good is the denominator and square. Okay, let's do it. So the numerator will be just, you can just copy the denominator guy here. Raise to the power 2. Okay. Maybe we just do step by step because our mind, we cannot. We do the numerator first. Numerator. Okay. Because our mind cannot denominator. The numerator is just, the numerator will be just this over this, okay? And denominator will be, okay, not that difficult, is S2 over N1 square, and this will be divided by N1 minus 1, okay, plus, again, bracket S2 over N2 square over N2 minus 1, okay? So this will be the formula, okay? And that means the V, okay, will be just the numerator divided by denominator. Okay. And once you're the V, then we can do whatever we want, right? That is something we want to do. Okay. And we can do the p-value and the t-test again, okay, more quickly. Don't want to hold you too long. So the left tail will just t this, right? And you take this one, the t-value, right? The degree of freedom is, this guy is 17. So we get it smaller, so put 17 here and true. Want to be round down is the function where you will get the number. So if you really want to have rely on this function, okay? So 1 minus this guy, right? And 2 times this guy, a smaller one. Okay. So we can confirm what we have done. Let me get smaller. We can confirm we have done using the t-test. Array 1, array 2, okay. And we have 1 tail, we have 2 to 3. Okay. They're slightly different, but it shouldn't be an issue. And we have a t-test. 1 tail, 2 tail, 2 tail. Okay, so that is the only difficult part is this guy. Okay. But you can easily check how we work it out. That's how you S1 over N1 plus S2 square over N2 square square, and then this will be S1 over N1 square divided by N1 minus 1. Same for that. Okay, so there's some slightly difference, but should not be an issue. Okay, so how you do the, I'm not going to do the paired population because same as 1 tail. Okay, you should be able to do that. We can do it next time, don't worry. But that's what I have today. I stay around to answer any question you might have, but you shouldn't be concerned for you. at this moment. But I around, you can stay around if you need my help further. So I hope, I upload this file to the Blackboard again. Okay, don't worry. But in case you need help, just ask me. But nothing but just input the bunch of formula here. Okay. So I will see you next week. Enjoy the holiday, your long holiday, right? Except those people who have class on Friday, but otherwise you have a long holiday. So I see you. In case of a question, just ask me. I'm just stay around until 10:30.